problem is called unique paths. We are a robot on an m times n grid, and the robot is initially located on the top left corner. So basically first row, first column. The robot tries to move to the bottom right corner, last row, last column, and the robot can only move either down or right at any point in time. So we can either go like this down, or basically to the right. Given the two integers m and n, we have to return the number of all possible unique paths that robot can take to reach the bottom right corner. The test cases are generated so that the answer will be less than or equal to 2 times 10 to the 9. So basically, we have a grid 3 times 7, and the number of ways that we can reach this finish line is 28. And the robot can move here, or here, and then here again, and so on until it reaches the finish line. And there are a total 28 ways to do that. Before we get to the and you talk about how do we solve this, let's just see if there are any special requirements. As we can see, basically the m and n are just ranging from 1 to 100, so nothing special here. Now, basically, the number of this is kind of like immediately pointing us to recursion, the number of ways that we can reach a step by reach a position by starting in some other position. So to get to the recursion relation to recurrence, we'll basically have to think what are our decisions. So basically, we can move down, on, or right. So if we start our unique paths from 1 to 1, and we want to reach m and n, then we will have the base cases where basically first, if you are sending the coordinates x and y, which are just basically the number of rows that the robot is currently in and the number of columns that the robot is currently in, then we will check if x is larger than n, so which basically means that we are out of boundary, or if epsilon y is basically larger than n. In that case, we'll just return 0, because that's the number of ways that we can reach, because it's a base case and we haven't reached the finish. Otherwise, if we have an equal sign here and equal sign here, so we arrived at this position, then we will just return 1. And those are our two base cases. Now, for the recursion calls, we can basically just we'll call the helper function, which is just calculating the number of ways that we can reach any of the spots, any of the cells in the grid. We'll just increment the row. So the number of ways that we can reach the finish line by going down, plus the number of ways that we can reach the finish line by going left. So by going right, actually, by just incrementing epsilon plus 1. So the number of ways that we can reach the finish line starting from this position is equal. Basically, we have two sub problems that relate to the initial problem, pointing to the dynamic programming category. And the first sub problem is the number of ways that we can reach the finish line after we have moved down, plus the number of ways. The second sub-problem is the number of ways that we can reach the finish line by moving to the right. And basically, the base cases will eventually converge to the base cases and then just propagate up to the first call, and we'll get the number of ways that we can reach the finish line. Now, this will not perform really well because of the nature of the exhaustive search inside of the grip and the number of recursion calls that we have. So the solution would be to use memorization. So we'll basically track for each cell the number of ways that we can reach that cell, and then not calculating it again if we need it again. So for example, if we calculated this here by moving here and down here, we will not calculate it again when we move here if this call was the first one to be computed. So we will compute it only once. That will help us to kind of reduce the time and space complexity, while actually increasing the space complexity a bit, because we are now caching it inside of our hash map or any other data structure to track to cache the computations. But that's not that's basically our top down approach. We want our bottom up approach using tabulation, and tabulation is pretty easy. So the first thing that we have to find out are the initial values, the base cases, and the base cases are the following. To reach any cell inside of the first row, there are actually only one way to reach it, by just moving the row to the right. The same goes for the first column. To reach it, there are basically just one way for each of the columns, by just moving down, because we cannot go from the left, and here we cannot go from the down because it's from the upper row, because it's only one. It's the first row basically. So those will be the initial cases. Now the special cases, how do we calculate the number of ways that we can reach the cell? Well, the number of ways that we can reach the cell is basically we will have our DP that calculates the number of ways that we can reach a cell marked by I and J, basically the row and the column of the specific cell in the grid. And then we will just to find the number of cells that we can reach this cell here, we'll just add up the value that we have in the DP for our left column, and the value that we have inside our column up, basically in row up, basically a grid cell that's above our current cell that you are doing the computation for. So to find the DP ij, we will just basically add up ij minus 1, so basically our left, plus dp I minus 1j, the one that's above our cell. So that's basically the recurrence formula that we have, and we will just iterate over all of the rows and all of the columns to find out dp ij for each of the cells inside of the grid. Finally, we'll just return the last column in the last row that we have inside of the DP, because that will represent the number of ways that we can reach the finish line. Now, the time and space complexity are basically the product of the dimensions of the grid, so n times n. Now the question is, can we reduce the space complexity? Because time complexity we cannot reduce. We have to iterate over all of the potential cells, which are basically all of the cells inside the grid, because they can be a valid starting position to get to the finish line, or in an intermediate position, depending on the way how you look. So to get the space complexity, to reduce it, we will check what we are actually doing here. So we don't really need the first row if we are calculating the dp ij for the third row. So we only need the last, we need only the previous row. So we don't really need the matrix. So we will do the second dimensions, because these are basically the number of columns that we have for each of the rows. So each row is containing this many cells. So we'll just need the previous row. We don't need the whole matrix. And if we have the previous row, how can we calculate the current row? Well, basically, we know that we are, for each of the cell, we are adding the previous value. So we can just keep the dp, for example, dpj is the current cell, is the current column of the row that we are calculating. To get it, we can just add whatever we have for dpj minus 1, which represents our left cell, because the cell above will be already contained in the dpj, because it has been calculated from the previous row. So we'll just be continuing adding the left one, because the one above is already contained inside of it, because we are just overwriting the same row all over again. We're not using the matrix. We're just propagating the row down to the matrix while iterating over the dimensions. So in that case, we'll have a kind of linear space complexity proportional to the number of columns that we have. As discussed, we only basically need one row, and which is containing of n elements, basically the number of columns. And then we will just initialize that array to be 1, because that's, for the first row, the number of ways that we can reach any of the cell is only 1. We can just keep on moving to the right side until we reach the last cell. Next, we will iterate over the two dimensions, and we'll try to update the row, the values that we have for each of the columns inside of our one row. And to do that, we'll keep the current value that we have, and basically this represents the value that we are getting from the above, plus the one that we are getting from the left side. And to do that, we just have j minus 1. After we have iterated over both dimensions, we'll just return dp n minus 1, which represents the last value in the row, which is basically the last column. And because we have iterated over all the rows, it represents the last column, last row grid cell, which is the targeted end line that we are trying to get to.